So it's conservation energy, which is obviously an important topic. So we have too much time, but let's start with the first equation. So basically, you have assume you have charged particle. I mean, you can start with discrete particle, but then later on you just move it to a continuum limit, right? So originally, you have discrete particle, you have Q1 that moves one, Q2, moving on this two, and so on. You have n particles, right? Then the obviously within the space you have electric field, magnetic field, so E field, B field, whatever, right? But the energy, obviously, the change of energy is only due to E field because the power again, the power I think Dixon used, he doesn't have a symbol or power or P, whatever you use is a force dot into E. In that case, it would be sum of the force is Q times E. E is a function of x and t. So, and then obviously you need the position of that, the particle, but we'll not worry about that now because we'll move to the continuum limit. So that is right. And now you can combine this Q and V. This is sum, but then you can move to the continuum limit. So instead of having a Q, so you can now do a integration over space. Now you have all this Qi, Vi becomes having a delta function. So because in order to get that, you need to sum over. So you have Qi, Vi, delta function x minus whatever the location of the particle I also I, right, and then dot into E. Now you recognize this is just your current density. Yeah. So from discrete particles, you can know for the distribution of particle of current or charge continue of charge density and current density, that becomes just J as function x into dot into E. And that gives you the power of that this is the power that work on the particle, right? This is because this is the force that act on the charge. But this is if this is positive, it means you are giving more energy to the particle. If it is negative, then you're taking away the particle energy. And obviously that would be, you need to balance by the field, the energy of the field in order to have conservation energy. So that we'll see that by after we finish the derivation. Right? But this is a starting point. We write that this is the particle on, this is the power on the particle. Right? And the idea will start from that and derive what we call the Poynting theorem. It's basically the conservation of energy. And the same idea we can move on to conservation of momentum. And then there's angular momentum consideration also, but not within the section. Actually, Jackson moved that to the end of chapter problem, which I worked out the solution. So, that I can post that solution later because one of the homework problem actually asked about angular momentum. Jackson didn't cover in the section itself. But anyway, we'll do that. Well, last time we derived that the the work done or the change of energy of the particle, the work done to the particle is what we call it J dot E. Later on, we'll say that this is called the change of mechanical energy. That Jackson actually wrote it down later in 6.110. So this is the mechanical. Basically, the energy changes to the particle. So this is if this is positive, the particle energy will increase. Right. I think that Jackson's reason is he wanted to be going back to the microscopic equation before you define the mechanical energy, because if you're talking about a macroscopic system, then some of the energy people might not call it mechanical energy, might call it the heat energy or thermal energy, because some of this the work done to the microscopic particle may be random energy, and people usually define those as thermal energy. So there's another part that could be in the macroscopic description can be classified as thermal energy, but for microscopic system you can call it, because you're including everything as mechanical, then they are defined as mechanical energy. But anyway, this we can define this. Work on the Poynting theorem using macroscopic Maxwell equation, but you can always going back to microscopic, because what we can work on later on, we will need to assume the linear medium anyway. Yeah, and vacuum is obviously a linear medium, so vacuum will the derivation for vacuum is just straightforward. It's just the same. Okay, so we'll use the macroscopic Maxwell equation in particular. For this equation, you use the Ampere's law, so you spell H is J plus positive D positive T. Right. So now you have a J here, so you substitute J equals to cal H minus D positive D, and dot into E. Okay, that's just substitution. Now the next step, you have the two terms. For this term, you have curl H dot E, and what you want is a total derivative. Later on, will actually will becomes a divergence, and you can look up a vector identity that has that a total derivative, and one of the term will be curl H dot E. I mean the formula of obvious doesn't need to be E, H and E, any vectors you define. And the vector identity that you can look up from the table is we have one entry. We have divergence A cos B equals to B dot curl A and minus A dot curl B. So this is just the vector identity that that apply to any vector. So you just apply to here. So you want your curl H dot E. So it's like this one. You have a curl. I mean, either one should be fine, but I mean, it whichever one you identify as actual E, just change the order of A and B. So let's see what Jackson later. The quantity that we define will be E cos H. So A will be E, B will be H. So A will be E, B will be H. So this one is like this one. So you move this to the one side and move this to the other side. Okay. So A is E, so follow this one. So the first term will be so B will be H, so H dot curl of E, which is this term, and then minus this one, minus divergence of E cos H. Okay, so this is this one changed with this one. I mean, this one dot into E changed to this one. Okay, and then minus this one. Okay. Now you have the total derivative here. I mean, total derivative of, in terms of spatial derivative. So this is a total divergence. Now, for this one, you can use the Faraday's law. Curl E is minus partial B partial T. So now, so it becomes minus. This is minus. This is minus. Everything is minus. Okay, we have divergence E cos H. And then you take the minus sign out, so you have what is the E dot D positive? That doesn't matter which order, and this is H dot partial B partial. After you use the Faraday's. Okay. Now, this is as far as we can go for using the macroscopic equation, because these terms H and B and E and D, the relationship between them are not given yet, right? And so we need to make assumption now to further specify the form. Otherwise, this would be the final form that we'll do. And so, and in that case, so the integram, both are integrating over a volume. So you can say that this is an arbitrary volume. So you can say the integram would be the same. So J dot E equals to minus of this one. Okay, so that would be the energy conservation, which is as general as it can be. But to further the derivation, you just assume that the D is proportional to E, linearly proportional to E, and H is linearly proportional to E. And so this will be, then the derivative will be 1/2. Take the time derivative out, it would be E dot H divided by 2. And likewise, the other term is the same. So that would be for linear, I should say, for linear. Then this is minus divergence E cos H, and then plus 1/2 of partial T E dot H, E dot D plus H dot D. Okay. That is so the reason to do that is now you take the time derivative as the total time derivative of a quantity. This is quantity E dot D plus X dot T, X dot B. Then you can take that time derivative out of the integration. So write it as the first term would be minus d dt. After you take it out of the integration, you integrate over all space. So what is left is time. So this partial derivative becomes a total derivative time. And then that one is integrate e dot d plus h dot b, 1/2 of that. Okay, so integrate the whole thing and take the time derivative. And the last term is minus just divergence of E cos H. Okay. Now the left-hand side is ultimately this mechanical energy, and there's another ddt term, and you can interpret now this is the field energy. This after the integration is the E of the field, because all the integrams involve the field. There's you have electric field, the displacement, the H field, and the B field. So these are the field energy, and the time derivative of the field energy is given by that, and this is the time derivative of the mechanical energy. And finally, you have a total divergence, and you can keep it as a total divergence, and write like that total derivative. I mean the integration of the total derivative, but then the total derivative after you integration, you can use the divergence theorem also. So this term, or the whole thing, can continue by as ddt of B field, and this one becomes a minus surface integral. Whatever the volume, this is, we first define the volume. This is the surface of that volume. H and into the normal direction, area integration. Okay. No. That's a negative side. Okay. So so that is that's, I mean, similar to 6110107, or I mean the or 61111. After you define this S vector, so this is defined as your S vector, which is called the Poynting vector. The Poynting vector is defined as E cos H, and the interpretation is energy conservation. Of course, Jackson, now after this step, going back to microscopic equations, basically just H is B over mu 0, and D is epsilon 0 times E. Going back to microscopy and call that mechanical energy, but if you don't be that specific, then we can just move that term to the other side, so ddt of E mechanical. E field equals to minus this S dot NDA. Okay, so, and then you interpret that as a conservation energy. This is now the 6111. Okay, and this is obviously the again, this is the mechanical energy, and this maybe include the thermal energy, and then this is the energy of the field. You take the total change of this one, that's equals to the surface integral as this S vector dot to the normal and then do the surface integral. Now you can, from this equation, if you interpret that as conservation energy, then the physical meaning of S is simply the so-called energy flux, right? It's like if this is B, then this integral will be magnetic flux, and of course, if there's total closed volume, that flux will be zero for magnetic field, or whatever quantity doing something like that is the flux, right? So this is basically the and then if this is positive, then it means the total quantity will be negative. The energy of the mechanical energy plus field energy will decrease. So this integral itself represents the energy that go out of the volume. So basically, you have volume V, and then a surface S, right? And inside you have if you do the integration of mechanical energy, and you get the mechanical energy and field energy by doing this integral. So the field energy is given by this integral. The mechanical energy will be integration of all the kinetic energy, all the particle, microscopic particle, right? And now this change is given by the energy that whether it's going out or going in. For some part of the surface, it might be going out. The other part will be going in. Going in or going out depends on whether the dot product with the normal is positive or negative. If S dot N is positive, then it's going out. If S dot N is negative, it's going in, right? So in this equation, you interpret that S is as the energy flux. Energy flux means that you need to, the energy, you multiply by the area, will give you the energy per time, the change of energy per time. So the unit for S would be energy per area per time. Okay, so that will give you the energy flux. Okay, and so that in a sense is an equation of conservation of energy. All right, and that is the total energy. But this volume can be arbitrary, so you can also write down the microscopic energy density, microscopic energy conservation by equating the integram. So like you have this one, and now you can define this as energy density. I think Jackson got U, whatever that is, U, just U. Like this, call this including the 1/2 factor, this U. That's the energy density of the field. Right? If you write it like that, then the integram will be J dot E equals to, you have a minus divergence of S, and then a minus partial T U. Okay, so that would be the microscopic equation, and this is the equation. Yeah, this is equation 6.108 that in different sign, and then put it in the other side. Basically, if you rewrite it like Jackson, this is partial U partial T plus divergence S equals to minus J dot E. Okay, so you interpret that as a conservation law in the sense of so-called continuity equation. So this is the energy density, this is the energy flux. So if the right-hand side is zero, the energy is energy of the field will be conserved. So this is the field energy density. S is the energy flux due to the field because S is given by E cos H both for the field. So if you don't have J dot E, if J dot E is 0, then energy is just moving around. The energy density move around in space using the energy flux, the Poynting flux, right? Just like the continuity equation of charge. So if you have continuity of charge, because the charge will not be created or dissipated, so you have partial well positive plus divergence J is 0. This is the continuity equation for charge. This is charge density. This is the current density. Current density you can interpret it as charge flux, right? So now this is the energy density. This is the energy flux, and so but the right hand side may not be 0. So this energy equation has a source or sink, depends on the sign of the right hand side, right? If it's negative, obviously the energy will be dissipated from the field. If it's positive, then energy will be added to the field. Okay, so this is a microscopic equation. This will be your macroscopic equation. Okay, and so that would be all the conservation of energy equation. Is that okay? Up to here? Is that okay? Yeah. So up to here, so there are a few things you want to memorize. Yes, a few things you need to memorize is the definition of S. S is E cos H. For microscopic field, it would be E cos B divided by mu 0 for vacuum field, right? And then the field energy, and field energy is 1/2 of E dot D plus H of B, which we learned before from electrostatic and magnetostatic. We divide this before, right? But this is total dynamic situation to define this energy density. And then for vacuum, obviously, just change that. D will be epsilon 0 E, so this will be epsilon 0 E squared. And H is B over mu 0, this will be 1 over mu 0 B squared. Okay, and then divided by 1/2 is the energy density. Okay, so these are the things that go into the energy conservation. All right.